So thank you for having me. I'm going to give a talk about how Rust makes open source embedded drivers easy. This talk will be an introductory talk. So during GOSIM, we had a lot of in-depth talks. I'll try to give a more for beginners friendly talk. So this talk is aimed at either people who are Rust developers but have never developed with Rust embedded yet and want to try out embedded, or embedded developers that have not yet tried using Rust but want to use Rust maybe. So I hope I'll inspire you to give it a try. If you're already a Rust embedded developer, then maybe this talk will not give you anything new except maybe inspire you a little bit. This talk is split in 3 parts. So I'm going to give an introduction to embedded and drivers. We'll write a platform-independent Rust driver together during this talk. And I'll also explain why open source drivers are hard to find and use specifically. So why open source drivers are a particular nasty problem to solve and how Rust has done this. So in order to explain this, I'll be using 3 different types of platforms to illustrate the point. So I'll be comparing Arduino, which is probably you're already familiar with it, used by lots of hobbyists to create their own hardware of software for boards that already exist. Zephyr, which is also used in a more professional context. It's also part of the Linux Foundation. And it's used, for example, by companies like Apple to make electronics. And finally, of course, the Rust ecosystem. So why am I the person that should be giving a talk about this? So hello, my name is Wouter Geraedts. I'm a freelance embedded engineer and I have my own company. So what I do for a few other companies is I help with software development in C, but also in Rust. But I also do electronics board design, help with manufacture. Some of the manufacturer is outsourced to countries like China. And I also help with when they have a specific hard problem to solve. Like their engineers have worked a month on some reliability issue, and then they ask me, Wouter, can you find, is this a hardware problem? Is this a software problem? And then most often I can find it, sometimes not. Also, like was already explained, I am a board member of a foundation called RustNL. And what we do is we try to organize conferences and meetups in the Netherlands. And we also do some other supportive Rust work. And I'm very proud to have been able to help with co-hosting GOSIM this year in the Dutch city of Delft. We're also doing something special. So next year, we're going to have a conference in the Netherlands again, but this time it will be a full week. And during this conference, we'll have normal talks at the conference, we'll have workshops, but we'll also have the 10-year celebration of Rust. And as part of that, we'll also have, for the first time in 6 years, the Rust All Hands, where a bunch of people from the core teams will visit the Netherlands and talk about the project. And there will also be a bunch of unconferences. If you want to visit, it's already possible to buy early bird tickets for the conference itself. If you want to join the All Hands, you should have already received an email from the core team that you can indicate your interest, and that will be handled separately. If you want to sponsor, we're also still looking for sponsors. Yeah, I think there are lots of opportunities to get great exposure at this conference. But back to embedded. So I make electronics. This is an example of a board that I made, and I'll briefly show it in just a moment. Yes. Sorry, I needed 2 hands for that. So it's running here. I'll not give any context on what this electronics does, but do know it is running a full Rust stack. It will come back in the talk later on as well. So let's first give a definition. What even is a driver? So I just looked up some definition online. This is not necessarily my definition, but it's a definition. So here it states, a driver provides a software interface to hardware devices, enabling computer programs to access hardware functions without needing to know precise details about the hardware being used. So it says something about you want to make software and you have separate hardware devices that you need to communicate to. This can take many forms. Specifically for this talk, I am interested in devices that are external to your microcontroller. There's also a notion of drivers for devices within your microcontroller. We'll briefly talk about that as well, but that's not the focus of this talk. So a driver communicates with the device through a communications subsystem to which the hardware connects. So this, in schematic form, this looks like this. We have a microcontroller. We have a processor within the microcontroller that runs your software. We have a communication subsystem, and it's able to talk to some external device over a bus somehow. Concretely, what this looks like is in the middle, I have a device. On the right, I have a microcontroller, and there is some copper between the two, and they're able to send signals to each other. Examples of these devices that you might want to use can be, well, they can be anything, can even be other microcontrollers, but more reasonable, they are like accelerometers to measure movement or acceleration. They are like clocks, they are like Ethernet if you want internet, can be radio transceivers, can be radars, can be a whole bunch of things. So for communication, what do we actually talk over those copper lines? So there are a few winners in this regard, as in most chips use these communication standards to talk to your microcontroller. They are SPI, R2C, or UART. So that means that the bus part of the schematic is one of those three, like 90% of the time. So I'll use SPI as an example to briefly illustrate what that looks like. So we have, in the case of SPI, either 3 or 4 copper lines. And they are as follows. You have a controller, which is the microcontroller, and the peripheral, which is the external device. The controller sends a clock signal to the peripheral device, and you have 2 data lines, one going each way, over which some data is being sent on the timing of the clock signal. And then we fourth have a chip select copper line that signals that a specific chip is being used if you have multiple devices connected to this bus. Concretely, on the right, you see a clock signal going up and down, and for every time that it goes up, so you have a rising edge, so it goes from 0 volts to say 3.3 volts, both the controller and the peripheral read from the data bus what's on the data line, and it will keep that somewhere in memory and pass that over to the processor. So we do not have one copper line. We have either 3 or 4 copper lines if we have SPI. So let's zoom in a bit. How does this concretely look like? So this is a view of the electronic design of the board. And let's zoom in on the microcontroller part of this board. So we zoom in on the microcontroller. Here you see the different pads to which it's connected to the board. And then we have the chip etched away with some solvent. You see on the external periphery of this image the pads, and you see tiny gold wires going to the silicon. And these attach to the edge of the silicon. This is also with some etching away layers by layers of this chip. And on the edges you see these square blocks to which these gold wires connect. And these are actually the transistors pulling those copper lines either down to 0 volts or up to 3.3 volts, depending on what your voltage is. We have these black areas, those are the memories, the various memories in this chipset. And then in the middle, we have this entire spaghetti part of transistors, which does not really seem to make sense, but it's actually auto-generated, synthesized, according to the definition of the vendor. All the other parts on the edges are like images that are bought in by the company that made this chip. As an aside, who knows what chip this is from purely the image? No one? Okay. So this is the RP2040 from the Raspberry Pi Foundation. You can even see, well, it's not really visible on the screen here, it says RP2. So it's actually on the image itself what chip it is. And the Raspberry Pi Foundation itself, they also give an image of what's actually on the silicon. So they say here, we have 2 processors in here. So Proc 0 and Proc 1. And we have a SPI peripheral here, meaning these parts run the software and they talk to this SPI peripheral here, and that peripheral decides when those copper lines should be pulled up or low. This schematic is a bit of a generalization. In fact, that spaghetti has everything going everywhere and not necessarily constrained to those boxes that they use here, but it's nice for an illustration purpose. So how does the processor actually tell this other piece of logic how to, what it needs to send over the SPI bus? So on the right, you see a schematic from the datasheet of a STM32 microcontroller, and the processor is here indicated in green, and the memory is indicated, various memories like volatile memory and non-volatile memory, flash and RAM, in yellow here. And if you do some mathematical operation and you want to store it in the memory, you just say, write it to this address, right? So you have a pointer maybe somewhere and you can write memory to it. But if you use a different address that's not actually pointing to those various memories, you go via an internal bus and you end up at a specific part of electronics that manages the SPI bus. So I indicate this here in the schematic via this small black line, that these 2 are connected and they talk to each other as well. So that means that there are also drivers managing this part of the process. That's not necessarily the point of this talk, but note there are also drivers involved there. So the datasheet also specifically says what memory range should be used to talk to this specific device. So here in the same datasheet, you see if you use something starting with 0x40013000, then you end up with the SPI1 peripheral. And there is also SPI2 and SPI3, multiple instances of the same peripheral. And then you have another page describing exactly what each bit in these registers means. So here we have 32 bits registers. So you have CR1, 32 bits, and there's each bit means something in this register. So that's all well and good. We now know in theory how we control this extra device in the microcontroller, but given these embedded platforms, Arduino, Zephyr, Rust, how does this actually get accessed within the software? So let's first take a look at Zephyr, how they do it. So again, given these registers that they're 32 bits and that you have specific bits that you want to change, what they do is they find a C struct, and for each register, they say, okay, here we have 32 bits, they mean something, but the control register one is at the top, and then comes 2, and in the middle we have a few reserved registers for which we don't necessarily know what they do. And then if you want to control the SPI peripheral, you just need this definition and write memory somewhere. Where do you need to write it? So Zephyr is part of the Linux Foundation. They have also some similarities to Linux. So they use also the device tree source system to define where these things are in memory. So here you see for SPI1, the address again, for where this struct is actually located. So if you write to an instance of SPI1, given the format in that struct, you end up at the correct address. So how does Rust do this typically? Depends a bit on the crate. So other talks also briefly mentioned this. So most peripheral access crates, as they're called, use an XML format called SVD. And it also enumerates what registers there are and what each bit means. And the nice thing is, this is provided by the vendor, so there's not as much work. Sometimes there are errors in there, so we need to patch these files quite regularly. but they also have nice descriptions in them for what each bit means. So, and maybe even an enumeration of what each value means. So that means that we can generate code automatically from this. So we use the macro system and maybe some other utilities to generate compliant Rust code that's somewhat type safe. And you can just, for example, in the right bottom corner, see that you can set a strongly typed enum to a register or part of a register. And internally, there's actually code doing like bit masks and those kinds of things. So we talked about how the platforms access the bus peripheral, but how do they expose it to the end user or the driver implementer? So let's look at Arduino. So Arduino is a bit infamous of its not suitability for professional work, let's say. So they have this documentation page for all SPI buses. So if you have a concept of an SPI in a chipset, it needs to adhere to this standard. And they describe a little bit what each function should do, but not really. But at least they say every Arduino core should implement something like this. And then giving Arduino core, by the way, Arduino core is the name for Arduino implementation for a specific chipset. And for a specific chipset, in this case an AVR chipset, for begin transaction, which is one of the functions that you should implement if you want to expose SPI, they have you can see here they use, like, they read the status register and they do mask and they set register. So that's all as expected. But what I want to point attention to is three things. First, SPI settings is Arduino core specific, meaning if you want to use this function for, if say you write a driver, you want to use this function and you go to a different core, it might not work. Secondly, this is a header file with an inline static, meaning this is the entire type definition. So there's no like generic header defining the function prototype, meaning they can just do something else as they like, which gives them ultimate flexibility, but is also, again, does not enforce that it's the same standard. And finally, it's not necessarily visible on this slide, but there's no notion of preemption in Arduino. So basically all these implementations, if they take some time, they are blocking and pulling. Meaning that if you have a battery-powered application, you are wasting quite a bit of power. Let's see how Zephyr does the same thing. So Zephyr has nicer documentation. They write exactly what you need to know to implement this. Not maybe everything, but most of the things. And most notably, they have this generic driver/spi.h header, which defines all these types. And then if I want to implement SPI buses, I just need to use this header and instantiate a static const instance of this SPI driver API struct and assign my function pointers to it. And the driver just works. This is exactly how you would want to do this in C. And also because it's static const, probably the compiler is able to make this a zero cost abstraction. Also, you get a bunch of free functions, mostly following from the using of the device tree source files, which is also very nice. So now, how does Rust do the same thing? And this is where it becomes special. So I already explained that we had XML files and SVDs that generate Rust code. This Rust code that's generated is put into a peripheral access crate, as it's called, so a PAC. And for every chipset supported by the Rust ecosystem, there is at least one, sometimes more. Then you have the Embedded Hall Working Group have various subgroups, and they implement a high-level version called a hardware abstraction layer that makes using these devices in your microcontroller easier, more convenient, at least for the general use cases. So for STM32, this one is called STM32 Hall. And these implementations of these high-level convenience functions are adhere to traits implemented in a special crate called Embedded Hall, which defines what all crates should implement if they are able to. And this is very special because that means that if I have a driver, I can just use the embedded Hall crate, and basically it works on any Hall crate. So basically that means that it runs on any chip that implements embedded Hall. So again, I can use then any device on any microcontroller. And this is not at all the case for most other ecosystems out there. So how does this concretely look like? So let's look at the trait for SPI buses. You also have traits for I2C, for example, in the same manner. So you need to implement at least these functions to be considered a valid SPI bus. And for each of these functions, there is also nice documentation saying what contract you should adhere to. Notably, for example, here it mentions something about if a certain buffer is smaller than the other, it will ignore or either pad it with implementation-defined bytes. This is missing in the Zephyr documentation. So what happens there if you do the same thing, like make one of the buffers shorter, is implementation-defined, basically. So let's look how you would implement this as a Hell crate. So as a quick example here, this is from a STM32. So if I want to transfer, so SPI, basically everything is a transfer. First, in STM32, you write the bytes that you want to write, and then you read it, and because this is this version is a polling interface, you basically yield an error, either saying I've done the operation successfully or please check it back again later. That's the MB block in there. And then as an example, I have here the writing also, and it starts with reading the status register, and then it will check a bunch of bits, and then if it's not yet done, it will return, okay, please check again later. But notably, it will make nice error types for error conditions. So Rust will see error overrun if there's an overrun, mode fault if there's a mode fault, CRC if there's a CRC error, and in the end, it will try to write the data if everything is okay. And this is really readable code. So again, why is this great? I think it's really worth to stand still at this point and consider this. It makes a foundation for building an agnostic ecosystem for platform agnostic drivers. Again, which means any microcontroller for which embedded Hall is implemented can use any driver. This is huge. That means that I can just go to crates.io and download any driver, and it will run on any microcontroller. They do this by defining a few specific things. So how delays work, how digital I/O pins work, how SPI buses work, how I2C works, and how pulse width modulation works. Why only these 5 concepts and not, say, for example, I2S, QSPI, SSI, etc.? And that means, the reason for that is a majority of devices use SPI and I2C, and embedded Hall decided, let's just focus on stuff that's used a lot to make it easy, and leave the hard stuff, so the implementation specific stuff, or the stuff that's not used a lot, to other crates. This is also implemented in other crates. So for example, CAN buses are implemented in embedded CAN. I/O buffers are, like UART, are implemented in embedded I/O. We have a crate for smart LEDs, and we have a special crate for rendering images to embedded graphic displays as well. And also, we have a nice mocking framework. So if you have a driver that implements embedded Hall, you can use embedded Hall mock to check whether the correct register reads and writes have been performed, or at least transfers have been performed, let's say, in the case of SPI. So what I do in a professional context is I download the vendor-provided driver and application, if there's an example application, and I put probes on the copper lines. I record the communication that the example executes, and I'll implement then my Rust driver and use embedded Hall mock to validate that my Rust driver is able to replicate the vendor-approved behavior from the example. And it's a really nice way to validate that it's running correctly. Okay, so now for something different, let's go make a driver together. So I already showed this one. So this is device that also has a speaker. I did not enable it for this demo because I thought sounds would be maybe a bit annoying. But during the development of this device, I noticed that the amplifier was not very good at making sound, that because the speaker is really small. I'll not go into detail about why that is, but let's say I needed a better amplifier. So I eventually ended up with this Texas Instruments amplifier. On the right here, you can see a symbol of a speaker, the chip, and on the bottom left corner, you see SPI port, and we'll use that to control this chipset. So for audio systems, we need to have two buses. So audio is typically transmitted over I2S, and we'll use SPI to actually control the registers. But sending audio is more of a task of the microcontroller and is a pretty standardized communication method. You just basically stream your audio bytes. So for this driver, we'll mostly consider the communication bus to set commands, and not so much are interested in how to send audio. We'll use the SPI bus to configure at what clock frequency I2S should be operating, but not send any audio itself. So how does this look like? Again, drivers of this chipset also has memory, and if we set bits in this memory, the chip will behave differently. So it's a very similar concept. So again, we have a series of registers, and we have for each register, for each bit, defined semantics. And also the datasheet specifies how you should use the SPI bus to actually read and write to registers. Right? SPI is only for sending bytes or bits even over a bus, not necessarily something about register. So we first need to define how do we read and write from a register. It's actually pretty simple. So this first 7 bits that you send are the register that you want to read or write to. The 8th bit is whether you want to write, so you write a 0 in that case, or a 1, and you want to read. And if you want to write, you then follow it up with 8 bits of data that you want to send. And if you want to read, you will get back 8 bits that you want to receive. For I2C, this chip also supports I2C. It's completely different. But for SPI, you only send, you can read and write 1 register at a time. In Rust, we implement this as follows. So we have a read register and a write register function, which corresponds to the embedded HAL. To something I'll show later. Sorry, I was confused. So for reading a register, we will first make a buffer, bit shift the register, and then write a 1 to the 8th bit. So that's a read operation. We make some dummy data, then we do a transfer, and then in the dummy byte, our data will be set and we will return it. And for write register, we do the same thing. First 7 bits are the register, we'll leave the 8th bit at 0, and then we'll write the value. It's really simple. And then I'll use a crate from a friend of mine, a device driver. Dion made this, and it allows me to, similar to an SVD file, make a YAML file, which describes each register. So I'll give a nice description to each register. I'll say what each bit means, and I can even define, for example, for the power control register, I can define the field called mode, and it has the values active, mute, software shutdown, and load diagnostics active. And then if I call this macro, basically almost the only code that you need, it will automatically generate the Rust documentation, the Rust code, and strongly typed enums to set values in registers. So that's very nice. It saves a lot of work. Basically, the most work is writing that YAML file, which is 1,000 lines of code or something. Or not even code, just descriptive registers. So how do we use it? So you can just write simple stuff like, I have the power control register, I want to write to it, I have this enum, I want to set the mode to mute, and then you call it and it happens. This is not necessarily really useful for an end user, the user would have to read all the register definition to understand what is going on. So instead, we're also going to define some high-level convenience functions. So what do you want from an amplifier? You want to change the volume, probably. So this function either mutes the sound or sets the volume to a specific level. Okay, so in order to make it open source, we need to do a few extra things. I'll not do them in this presentation. We need to make a nice runnable example. We need to add tests with embedded HAL mock. We need to add a README. We need to add an open source license, of course. We need to add description tags and category for cargo. And we need to run cargo publish. And then we'll have a nice open source driver. I want to give special attention to a nice runnable example. If you have like a development board that someone could buy and run your code to just validate that your code is good, that's a really nice way to encourage people to use your driver. Okay, so we now wrote the driver. I'll now shift focus a little bit and focus on my thesis, namely open source drivers are hard, but Rust is making it easy. So first I need to put some light on why exactly open source drivers are a hard problem. So the first is portability. It's hard to run your driver on any chipset. So like I showed you, Arduino cores are not necessarily portable. So if you implement for a specific Arduino core, whether it works on another core is an open question. You need to check it out. And also your driver is made for a specific ecosystem. So I did not show this, but Zephyr drivers are very tightly bound to Zephyr. Aside from the struct definition, internally it probably uses some threading operations, say for example, that are specific to Zephyr. And I don't have those definitions in any other platform. Yeah, Rust, however, because embedded HAL is such a generic concept, it can run anywhere. It's not assuming anything about what your system looks like. So you can run an embedded HAL driver on bare metal. You don't need an operating system, but you could use Arctic or Embassy Executor. You could even run it in user space Linux, say if you have a Raspberry Pi. You can run it on FreeRTOS. You can even run it on Zephyr. There are Zephyr bindings for Rust. So yeah, why even make C drivers for Zephyr? But you can also use a proprietary operating system. So I have implemented Rust drivers for closed source operating systems that are specific to a customer. And that's no problem at all. Second point, version control and dependency management. I see very often as a professional in the field that previous maintainers, previous developers of a project just copy and paste open source drivers into their project, into a subfolder, and just change it until it works. Which is fine if you want to be productive and you want to get your project quickly going, but it has a lot of downsides. It's really hard to then, if you have an improvement, say, upstream it back again to the open source project, or the other way around. If the open source project has an update, how do you get it back into your changed monstrosity in your root folder? Also, I see a lot of Git submodules being used. Problem with that is how do you manage dependencies of your dependencies? And Zephyr uses West to, which is basically Git submodules with dependency management in there, which solves this partially. And for Rust, of course, we have cargo. So we can just let cargo keep track of the entire dependency chain. And we have nice SEM versioning, all kinds of things which tackle this specific problem. Third point, the language itself. C++ offer meager API guarantees. So opinion is split on this one, but personally as a professional, I see a lot of thread issues in embedded projects. So C has no notion of threading by itself. If you have a function, is it thread safe to call? Can you call it from an interrupt? It's unclear. Some projects either do this in documentation or make like a ISR safe version of a function, but it's not the standard at all. So it's really hard to judge whether you can call a function just looking at it. Memory management is, of course, the classic problem. Does it do allocations? Does it do weird memory accesses? You don't know, unless you look at the code, if you have the code. And lifetimes is also a problem. Is something that I give to a function, should I clean it? Should they clean it? When should it be cleaned? It's also, there are like C standards for this, but does the implementing party or the open source driver actually adhere to those standards? You don't know. Rust has some specific solutions for this. So we have send and sync. We have, for thread safety, we have opt-in allocations. So most embedded devices don't have this, but you can use it if you want. We have the unsafe keyword, and we have references and mutability for these problems. And finally, discoverability. Finding drivers online, open source drivers, is actually pretty hard. If you Google or use some search engine to find a driver, you need to be pretty specific, and often words conflate. So Zephyr has their own repository, of course, with their drivers. It's not many drivers. Yeah, Arduino is worse. But Rust has crates. The Rust embedded working group has awesome embedded Rust, which is a page dedicated to just summing up all the different efforts that are going on. And when I made this slide, there are 128 open source no std driver crates listed on this page, and I am sure that there are more. In conclusion, in the past, using open source drivers was hard with C and C++ and other operating systems, but Rust makes embedded easy. I think it's really important to value what a change this is. As a hobbyist, you can just run cargo add driver, you need to attach it, and it works. As a professional, if I want to make 1,000 pieces of a device, my time is more expensive than the production cost of those 1,000 units. So if I can find a nice Rust open source driver, but the chip is maybe a dollar more expensive than another chip, I'll use the more expensive chip because it saves the customer time and money. The main takeaway that I want to give you is it's really easy. Go make some Rust embedded projects. Go to the Rust embedded book. There's even a Chinese version, a translation of the book. So please look at that book to be inspired, and look at the awesome embedded Rust page to get inspired by all the various drivers that exist. And if you want to chat with the working group, I think the best place is Matrix. So that was my talk. Thank you for your time.